Is that okay with the lights? Okay, let's start the seminar of this week, our seminar from Sandoval Vallarta. We are very honored to have Professor Keith today with us. Keith, received a bachelor's degree in 1978 in mathematics from the University of Chicago and a master's degree in physics in the same year. And in 1981, a PhD in physics also from the University of Chicago. And his dissertation dealt with cosmology and particle physics. In 82 and 83, he was at CERN working with John Ellis, and he began his research on supersymmetry. His main research deals with particle physics and cosmology, Big Bang nucleosynthesis, particle dark matter, Big Bang baryogenesis, and inflation. And right now, Keith is professor at the University of Minnesota. He was made McKnight University professor in 1998. He has been recipient of the Hans Bethe Prize Award in 2018, Fellow of the American Physical Society in 2003, National Science Foundation Field Investigator Award in 1987 to 1994, and elected University of Minnesota Distinguished McKnight Professor, as I already said, in 1988 to the present moment. And he was granted the George W. Taylor Award for Distinguished Research in 1988, so we're going backwards in time, by the College of Science and Engineering at the University of Minnesota. And right now he's going to talk to us about his area of expertise, precisely, cosmology, BBN CMB connection, Big Bang nucleosynthesis, cosmic microwave background connection, post-Planck. Thanks.
It's a pleasure to be here. It's my first time in Mexico City. Nice to travel so far and not change the time. No jet lag, but I'm saying still getting used to the altitude. I'm going to talk to you about the current state of Big Bang nucleosynthesis primarily, and how it connects with the relation between that and microwave background radiation. I'll start out a little bit of more historical context. I'm assuming that people aren't very familiar with the subject. Start about talk about the connection between the CMB, so the two experiments there. WMAP is one of the premier experiments looking at microwave background anisotropies, and that was followed up with a much higher precision experiment called Planck, and that determines. I'll define these quantities, eta and omega b. H squared eta is baryon to photon ratio, essentially, the number of protons in the universe relative to the number of photons in the universe. And omega b is the fraction of critical density in the form of baryon, so protons and neutrons in the universe. And so omega in general, if omega is 1, the universe is on the cusp between being a closed universe and an open universe. And so we know from inflation, for example, and from the microwave background, that the total omega is 1, but only a small fraction of that is in the form of normal matter or baryonic matter. Almost all the source of energy in the universe is in what we call dark energy. Instead of that, you can just call it a cosmological constant, something that Einstein introduced early on to avoid the expansion of the universe. And the rest is dark matter, and this is only about 5% is in the form of baryon. Nucleosynthesis, so is the calculation of the abundances of the light elements in the early universe, and so to do that, you need to know something about the nuclear cross sections that go into that production. And so I'll tell you a little bit about that, and I'll tell you a little bit about some recent experiments that have been done and are being done to improve the accuracy of the calculations. And I'll talk about the observation, so I'll be concentrating on the three light elements that are relevant for nucleosynthesis, the deuterium abundance, the helium-4 abundance, and the lithium-7 abundance. Those are the ones that you connect up to the Big Bang. And then in the end, I'll talk a little bit about neutrinos and how you can use Big Bang nucleosynthesis to set constraints beyond the standard model physics and where things look for the future. So started with, these are the people that are really responsible not only for Big Bang nucleosynthesis, but for Big Bang theory in general. So usually the credit always goes to the professor. Here is George Gamow. Ralph Elfer was his student and Robert Herman was his postdoc. They were trying to do nucleosynthesis. They were trying to understand the origin of the elements that we see. And to do that, they thought we need to have nuclear reactions taking place. And so from that, they needed to have high densities, high temperatures, a lot of energy. And that led them to this idea, well, since the universe is expanding, perhaps in the past, it was once very hot and dense so that nuclear reactions can take place. These are the people that really are responsible. A lot of times, this is the set of people that get credit for alpha, beta, and gamma. Notice the irony there. So this is the paper from 1948, alpha, beta, and gamma. It's a real paper. When I was a student, I had the chance to meet Hans Bethe came to Chicago to give a colloquium, and he met with the students, and we had a chance to ask him in particular about this paper, because obviously it's a little bit funny how you get these three authors in that order. And very candidly, he said, well, actually, he didn't have anything to do with the paper. Gamow is a little bit of a jokester, and Gamow thought it would be funny to have a paper with alpha, beta, and gamma. And so he said he sent him the paper and asked if he would mind being a co-author. And they read through the paper. Of course, he's expert on the material as well. But he said, I didn't see anything obviously wrong with it, so I agreed. So this is what they were trying to do. This is a plot of the abundances as a function of the atomic weight in some sort of relative set of abundances. And they were trying to do some calculation. This curve is something that they were trying to cook up. It's not correct, but this is what they were trying to do. And through this model that they had, this Big Bang model that they actually didn't call it the Big Bang model. I don't know if you know the history. The competitive model at the time was the steady state model of Fred Hoyle and his collaborators. And it was actually Hoyle that named it. There was a radio program, and they were talking about cosmology, and Hoyle was explaining about his theory of steady state in a very scientific sounding name. And he said, it's silly Big Bang theory that Gamow is having. So he named it to make it sound silly. I don't know how that ended up. So this is really a more modern version of the abundances of the elements as a function of the atomic number again. And you see we have lots of hydrogen, helium, and then there's a big dip here, lithium, beryllium, and boron. I'll say a few words about beryllium and boron. Then you have everything else, and everything else really comes from stars. It has nothing to do with the Big Bang. You might make a completely negligible amount of carbon, but essentially all the rest of it comes from stars. So we can do a real easy back-of-the-envelope calculation, which is, they did it better at the time, but this is very simple. In their model, they knew that they needed to have temperatures above about 100 keV. That's just to have the nuclear reactions take place. And they knew from that meant that the time they had to do that was about 200 seconds. So they had some model of how the universe expands and cools. So they assumed it was hot in the beginning, it cools. And so they knew that if you waited longer than 200 seconds, the temperature would be below 100 keV. So they had 200 seconds to work with. And then they knew that the cross-section for the first link in the chain, protons plus neutrons making deuterium and a proton, a cross-section about 5 × 10⁻20 centimeters cubed per second. And from that, they could figure out the density of baryons you needed to have reactions take place. So the density of baryons, just 1 over sigma VT, about 10 to the 17 per cubic centimeter. It's not a lot. Right? That's what they figured you needed. You can also figure out today what the baryon density is just by looking at the sizes of galaxies and the density of galaxies. You can come up, again, just rough number, order of magnitude 10 to the minus 7 per cubic centimeter. And if you know that the density just scales with the expansion of the universe with the volume, which scales inversely with the temperature, so the baryon density would drop as the temperature dropped, as the temperature cubed. And so given those numbers, you can figure out the temperature that you would expect to have today by comparing these numbers, and it's about 10 degrees Kelvin. Very simple calculation. And so alpha, actually, this was not done with gamma. Gamma always gets the credit for this, but this was actually Alpha and Herman. Alpha came to gamma to say, I think our model predicts that there should be some leftover radiation in the universe. The temperature, actually, they had it better than this, as you'll see in a minute. And gamma, Scott, what are you wasting your time doing this? Who is ever going to measure a photon background temperature of 5 degrees? Go back and do something useful with your time. And we know how that turned out. This is the paper. This is really to me, it's an unbelievably amazing paper. 1948 again, just Alpha and Herman. And I'll pick a few quotes from here. So they're taking the matter density, rho m prime and rho r prime at the time of nucleosynthesis, so early on. And it's essentially the same argument I just made. They say, let's use that together with rho m double prime, which is the value of the matter density today. And they say that'll fix the radiation density today. And they say, which is perhaps the least well-known quantity. Of course, today, that's by far the best known quantity because it's measured by CMB experiments to extremely high precision. So that was their argument. And they came up with this. And somewhere, if I can, you see, they calculated 5 degrees. And they knew, okay, there are uncertainties. We don't know all the quantities in the theory. So to test the sensitivity to their choice of parameters, okay, it could be 1 degree. But basically, they're saying it's between 1 and 5 degrees, and the right result is 2.7. Not bad. So, as I say, this is done with considerably higher precision now. This is from Planck experiment. Well, the temperature is actually earlier than that. It's from Kobe, 2.7255. So you see the level of precision that the microwave background temperature, which means also the energy density in the microwave background, is known. And from the this is the spectrum of density fluctuations as measured by Planck, and the dots are the data. The blue curve that's going there, if you're not familiar with this, you might think, well, somebody just drew a line through all the points. There are 6 parameters, and then with those 6 parameters, the blue curve is calculated. And to see that it matches these observations to this kind of precision, again, is something absolutely remarkable. And from that, from the position of the bumps and wiggles, you can determine the baryon density today. And you see 0.02237, incredible accuracy. And then in terms of what I'll be talking about, eta, and I'll give you a little bit more relation between the two in a moment, but it's 6.12 times 10 to the minus 10. So that's 6.2 times 10 to the minus 10 baryons, protons and neutrons relative to the photon density. So back up a little bit again. So the conditions, this is again the basis for how you started the calculation. You assume at least that you had temperatures bigger than an MeV or so in the early universe. You can calculate the energy density and radiation. It's just a black body. And so T to the 4th, this is in units where h bar equals to c is equal to k, Boltzmann k is equal to 1. So the 2 is just a photon, the 2 degrees of freedom of a photon. 7/2 corresponds to E plus E minus, and if you're wondering why it's a fraction, it's because it's Fermi statistics relative to Bose statistics, and that gets you a factor of 7/8 relative to that. And there are 4 degrees of freedom. and also then the number of neutrinos comes in. And that gives you the radiation density, which dominates the energy density of the universe, and that controls how fast the universe is expanding. Eta, as I said, baryon to photon ratio is of order 10 to the minus 10. Now, of course, what you care about for nucleosynthesis are the neutrons and protons, and they're in equilibrium early on through the weak interactions. And the weak interactions actually, they're in equilibrium at high temperatures, and then at lower temperatures, below about an MeV, they drop out of equilibrium. And the reason is that the expansion rate, or the Hubble rate, is doing temperature squared over this is the Planck mass, not the proton mass. This is like square root of g Newton times t squared. And the weak interaction rate scales as t to the 5th times g Fermi squared. Weak interactions. And so you see that as you cool, eventually H becomes bigger than gamma. In other words, gamma you can think of as like 1 over the mean interaction time. So the time between interactions, 1 over H is like the age of the universe. And so you want to make sure that you have interactions happening within the lifetime of the universe. And when you drop out of equilibrium, that's no longer true. Even though the universe is getting older and you have more time, the rate of interactions drops faster. And so you stop having interactions. So initially, the number density of neutrons and protons are kept in equilibrium. So just the Boltzmann factor, the only thing that differentiates them is the mass difference between the neutron and proton. And then it frees out, that number becomes fixed, except for the fact that neutrons decay. So the number of neutrons decreases a little bit. Now, so nucleosynthesis starts when the rate of interactions to make deuterium is greater than the rate of interactions which destroy deuterium. So the total destruction of deuterium back to P plus N. And the rate of those interactions are given by the cross sections, which are the same, but the targets are different. So in this case, you care about the density of proton. In this case, you care about the density of photons. Of course, to break up the deuterium, you have to have photons of high enough energy to get past the binding energy of deuterium, which is about 2 MeV. So as the universe cools, this exponential factor becomes smaller and smaller. That is, the number of photons with high enough energy is how you're going out into the tail of that Bose distribution, and eventually that stops, and then nucleosynthesis starts. So nucleosynthesis begins when those rates are equal, or when this combination is of order 1, and that happens at about 1/10 of an MeV. And so from that, you can get what the neutron to proton ratio is. So you start with the fact that you're just using a Boltzmann factor for the ratio of n over p, e to the minus delta m over t. And then you factor in the fact that between an MeV and about 1/10 of an MeV, neutrons decay. You find that the number of the neutron to proton ratio is about 1/7, very roughly, and that gets you 25% helium by mass. And the rest, this would assume that all neutrons went into helium, but that's a good approximation since everything else is far below. So a little bit more accurate numbers, the freeze out actually happens at about 0.84 MeV. The deuterium bottleneck is lifted about 0.064 MeV. Neutron ratio drops from about 1.4, about 1.46 to about 1.7. This is the helium number density relative to hydrogen. And as I said, you can then plug that in and get the mass fraction of helium of 245. And that's still, this is done without a computer. This you can do just from knowing something about the cross sections and making an analytic approximation. You'll see this is actually extremely good. And this is a little bit of the chain. I'll show you the rest of the nucleosynthesis chain, but this is the part that we're talking about: neutrons and protons going to deuterium, and then deuterium going to tritium and helium-3, and eventually you see going to helium-4, which is in this sector the most tightly bound nucleus. And then even if you go a little bit past that, a lot of times you're coming back to helium-4. So as I said, it depends on knowing the nuclear cross sections. Typically in the reaction rate, this is the full set of reactions that get used. We go way past helium or way past lithium. I'll come back to that in a second. and each of these arrows is a separate nuclear reaction. It turns out there's really only 12 of them that have any kind of sizable impact on the result. So the other ones are there, just be careful, but these are the ones that actually determine the abundances of the light elements. And so here I show what 4 of them look like, and they're measured in various levels of accuracy. You should also pay attention. Sometimes it's linear scale, sometimes it's a log scale. You see this one in particular, which is B here, is BP gamma. So this is the deuteron plus a proton, making helium-3 and a photon. And this is the energy range of interest for nucleosynthesis, so about 1/10 of an MeV. And there wasn't a lot of data there, so there were a lot of uncertainties coming from this, which are a little bit buried because of this log scale. And so that's one of the places where there's been some recent progress. So why do you basically not make anything beyond this? Why doesn't it just keep going? Well, first of all, you see there's a gap at A=5. There is helium-5, but it's extremely unstable. Its lifetime, if I remember, something like 10⁻16 seconds. So you just don't have time to build up any kind of equilibrium abundance of this. It just decays right away. Nevertheless, you can get beyond helium-5, and you can make some lithium-6, not much, I'll say, and then you get to lithium-7. And then again, at mass 8, you have boron-8, beryllium-8, and lithium-8, which are also very unstable. This is, I think, a nuclear chart. So beryllium-8 is, again, extremely unstable, extremely short lifetime, even for laboratory measurements. The boron-8 and lithium-8 are, for laboratories, they're stable, but for nucleosynthesis, they're not, because their lifetimes are still far shorter than the few seconds or hundreds of seconds that you have to get nucleosynthesis. So you have another gap here, and then basically you just don't go beyond that. So then this is what happens. This is the temperature as a function. This is, well, time is going up this way. So from left to right, here you see the temperature dropping. It's in units of MeV. So we're starting with an MeV, 1/10 of an MeV. You see all the action starts at around 1/10 of an MeV. Hydrogen is up here. You see it basically on this scale of the plot, there's a little bit. That's when nucleosynthesis happens, and then it's constant. The neutron abundance drops. That's when the neutrons get absorbed into the light elements. And then this is when nucleosynthesis happens, and then we have neutron decay also happening as well. And then you see the other elements, the red dot dash, the helium abundance, which grows rapidly and then goes constant, and that's by far the dominant element that gets produced. And then you have these other things. One thing that can point out, for example, this is the lithium-7. What you're actually producing in the early universe is beryllium-7, which much later actually beta decays to lithium-7. So the lithium-7 here originally got produced as beryllium. So one of the things that came out very early is that, well, this didn't work for getting all the abundances, all the elements, and so there's a period of time in the 50s where people sort of gave up on BBN as a whole. Because it didn't work, and people shifted to stellar nucleosynthesis to account for the elements, correctly so. But there were some problems left over. Your stellar nucleosynthesis actually doesn't account for either deuterium or helium-4. You do make helium-4 in stars, but not at the level of 25%. Maybe 5% total. So what's measured in a lot of places is 30%. The 25% we'll see is coming from the Big Bang. Deuterium is even odder because it doesn't come from stars at all. It only gets destroyed in stars. So if you see any deuterium in nature, it had to come from the Big Bang. So that led back to a resurgence, but a more limited scope for nucleosynthesis, Big Bang nucleosynthesis, just getting these light elements. And this is the result of the BBN calculations. So as a function of the variant of proton ratio, helium-4 mass fraction. You see it's in that range of 23–25%. Deuterium abundance, these are all by number. In the level of about 10⁻⁴, 10⁻⁵, and lithium way down at -10. Now, since we have the microwave background measurements which fix eta, and that's at 6 times 10 minus 10. But effectively, in the standard model of nucleosynthesis, there are no free parameters anymore. You just do a calculation, you calculate your abundances, and you're done. Right? Now you have just straight predictions for lithium, helium-3, deuterium, and helium-4, and it's either right or wrong, or somewhere in between, maybe, but that's what you're left with. So recently I mentioned that there was some new cross-section measurements, and this is that one I pointed to. This is the DP gamma reaction, so production of helium-3, photoproduction of helium-3. And the new data are these red points that are sitting here, and they're really filling in that gap of where there was some data, but with large uncertainties and quite a bit of scatter. And so you see the red points really line up. These are the same thing, but just plotted on different scales. And this is about 2-3 years old, and there are a few other measurements that we're hoping that they make, because this does make a difference. So here is the effect on the uncertainty. So the primary uncertainties in the Big Bang calculations, I didn't say it, but let me back up. The thickness of all of these lines have to do with the uncertainties, and those uncertainties are in the nuclear rates that go in. There's really not very much else. In the case of helium, it's basically the neutron mean life. That's the only uncertainty that causes the thickness of this line. And you see there's a lot more uncertainty in lithium. And so that one measurement, that one cross-section measurement, you see that it takes you down from these dotted lines to the solid lines. So you had a pretty sizable improvement in the accuracy for deuterium, a little bit in helium-3, which you don't say you don't necessarily care that much, and some in lithium-7 might not care about that either, but this one we certainly do care about. And here it doesn't have any effect on helium, which anyway the uncertainty on helium has been multiplied by a factor of 10, just so that you can see it on this plot. Let me just say again, just because I'm going to use this nomenclature and use it already, but just to be a little bit more clear, the baryon density is just the mass of the nucleon, so proton-neutron mass, which is almost the same, times the number density of nucleons that you have in the universe, and that's how you define omega B. It's relative to a critical energy density that's used to close the universe. So that's just a number, which is scaled by the measurement of the Hubble parameter. This H is in units. It's in units of 100 kilometers per second per megaparsec, and should have a value. Little h should have a value of about 0.7. If you've heard about the controversy in the Hubble parameter, that gets you to a controversy in this little h between something like 0.67 and 0.72 or something. That's what we're talking about there. The density of photons today in the universe is 411 per kilocentimeter. That's given to you by the temperature of the microwave background. And so as a function of temperature, it's going as T cubed. T0 is the temperature of today. And so that's what rho B is, that's what omega B is. And then you can relate this ratio to omega B in a very simple way. So I'm going to interchange these two sort of at will, and they're related just by a numerical factor, 10 to the minus 8 or 10 to the 7, depending on what you're going. All right, let me move to the observations. Helium-4 is observed in extragalactic H2 regions. So these are in other galaxies and regions of ionized hydrogen gas. And you're looking at emission lines. And as I said a few times, you get about 25%. Lithium is observed in the atmosphere of stars in our own galaxy. They're called halo stars. So they're an old population of stars, sort of making a spherical shape around the center of the galaxy. Or they're small stars, relatively low mass stars, with an abundance of about 10 to the minus 10. Deuterium is best now observed in what are called quasar absorption systems at a level of about 3 times 10 to the minus 5. These are clouds of hydrogen gas that are sitting between us and a distant quasar, so along our line of sight. The quasar is the light bulb. The light is shining through the hydrogen clouds, and then you have some absorption. And from that absorption, you can determine the deuterium abundance. I'll show some figures for that effect. This is what the data looks like. So all the deuterium, as I said, is primordial. There are other ways to get the deuterium abundance, but they're not really primordial, and so they carry a lot more uncertainties. There are about 11 or 12 of these systems where deuterium has been extracted. So they're all relatively high redshifts of about 3. So they're at cosmological distances, and they're all at relatively, we would call this low metallicity. This is the oxygen abundance. This is the log of the oxygen abundance relative to the solar oxygen abundance. So -2 here would be 1% of the solar oxygen abundance. So this is these are systems where there hasn't been a lot of star formation, and so then you hope that the deuterium abundance that you measure there is related to the primordial abundance. So as I said, this is a quasar absorption spectrum, a little bit messy, but then you look at the place where the hydrogen line shows up, and so the hydrogen line here is this big that thing here that's been blown up, and the little dimple here at the side is the deuterium. So you need to have relatively clean measurements where you can really know what the density of hydrogen is, and then be able to determine the density of deuterium as well. And as I said, there's only a handful, a couple of handfuls of systems where this can be done. Several years ago, this is what the data looked like, and this was not a terribly great situation. The numbers are all in the right ballpark, but once these quasar absorption systems were measured much more systematically, the picture looks like this. That's the weighted mean of the data. So there's very little dispersion in the data, certainly all within uncertainties. And the BBN prediction is about 2.5 times 10 to the minus 5. And the observational average is also 2.55 times 10 to the minus 5. So again, within the uncertainty, and now the biggest uncertainty is in the calculation, not in the measurement. And so this is that same picture again, now with the, for your eye, this is the observational average of deuterium. So this tells you this. And I said before that we don't have a choice. This is the Planck measurement for the baryon density, and you see that nice agreement. So sometimes when you hear about the agreement between BBN and CMB, it's the fact that these 3 lines meet at a point. And so certainly within errors, and the errors are relatively small, the observational error is what is 1%. This is a great success. So let me move to helium. So as I said, helium is measured in emission lines, along with, again, metal tracers, and so it's either oxygen or hydrogen. So this is a function of the oxygen abundance, and this is the helium abundance. This is a sort of a bloated scale, just so that you see that there's just pretty much a uniform abundance of helium, no matter where you look. Solar is probably somewhere out here. It's at about 50. It's about 45 or 55. So these are all low metallicity objects. Not a lot of processing. This is very different from other systems. So normally, if you, as a function of the oxygen abundance, look at any other element that you're interested in, say here, nitrogen abundance, it always goes towards the origin. If you extrapolate back the low metallicity, it goes to the origin, and that makes sense because both of these things are made in stars. So if you go to the point where there were no stars, then there's no oxygen and there's no nitrogen. So deuterium didn't look like that, and helium didn't look like that. So forget the left side, it's probably crop it or something, but the right, this is sodium, I think. This is the helium is here. So these are the term diagram, which is just showing you the different levels. And so you have all of these. So you have a region where the helium is excited, and each time the helium drops down a level, you get an emission line. And so the bold ones here are the ones that are actually useful for the measurement of helium abundance of 66, 78 here, 70, 65. A recent one that's become very important that I'll make mention of is this one here, 10.830, which is an infrared line for that. So that you can then take a spectra of one of these galaxies, and you find that there are a number of helium lines here. There's a strong one right there, and another one here. So you take all of these into account, and now you have to have a model of what you're going to do with these things. So you measure a flux of helium, So for every wavelength of helium that you measure, you're going to measure a flux, and you scale it to some other line that you're looking at. In this case, the H beta line, so for hydrogen. And then you have a model that depends on the emissivities. It depends on other things that you might not be so interested in, the optical depth, the reddening, and of course the helium abundance. In the past, people would just basically use the fluxes. They take the two fluxes for 3 lines. You get 3 different helium abundances, and then you just average those, and that would be your helium abundance. And things have changed. Now you have a model. You try and get an estimate for what self-consistently of what all these parameters are, and you make a prediction for the fluxes, and then you compare that to the observed fluxes, and you develop a chi-squared, and then you can fix all of the parameters by minimizing the chi-squared. So when we started this, there were basically 8 parameters: the electron density, the underlying absorption, and helium underlying absorption, hydrogen, optical depth, temperature, and so forth, and of course the helium abundance. But you have 8 parameters, and we had only 9 observations, so it's a little bit delicate. There's been a lot of progress over the years. So new emissivities. I mentioned adding a new helium line. This is that infrared line. So now you have at least 10 lines to fit 8 parameters. And then since then, much more recently, we're going to add in a whole bunch of helium hydrogen lines. Much better predict what these things are. Okay. Is that?
I think it corrected itself.
Okay. Yeah. Okay. And so here's just an example of one object, dwarf galaxy BOP, and the kind when you had 9 lines and 8 parameters, the kind of uncertainties that you get, and in the recent work, all you have to do is just look at the drop in the uncertainties of these quantities, and that's telling you, the power of adding all these extra observations. And so there's a program now to try and do much higher quality observations for helium, getting a whole series of these lines, and hopefully getting the uncertainties down. This is what the data look like for systems that are useful. So you see the uncertainty. This is a blown up scale, but you see the size of the uncertainties here are relatively large. Nevertheless, you can extrapolate down to 0 metallicity and get a primordial helium abundance, which is very good agreement with that back of the envelope calculation I had before 24.5%. So that's where we are now. This uncertainty is dropped by a factor of about 3 by doing this this method. So this is where we're sitting for the helium abundance. So again, the prediction is really right there. The observations are there, so they're certainly in agreement. But you would like to have this band shrunk to be aligned like deuterium. There's good agreement, but we'd like it to be better. All right, lithium. Lithium is a more complicated one. So this is here Li in brackets is the lithium abundance. It's log of the lithium abundance relative in absolute terms plus 12. Don't ask me why these notations come about. The astronomers like to do these kind of things. So this is 2 here is 10 to the minus 10 in the abundance. Okay. And that's essentially what you get from Big Bang nucleosynthesis. Well, you get a little bit more than that. I'll describe. But at the higher temperatures here, the lithium abundance is expected to represent the initial abundance of the stars. At least that was the idea initially. At lower temperatures, the convection zone in the star is much thicker, and so the lithium gets exposed to the hot interiors of the stars and destroys the lithium. So only when the convection zone is thin and the temperatures are not getting to the point where you can destroy the lithium in the interior that you expected to get uniform abundance. This is a function of the iron abundance. Again, now back into the log relative to solar, so this is 1% solar. And here again, this is the same set of points that you see here. At higher metallicities, you have to go to higher temperatures. So these stars are all at bigger than 5,500, I think, here. And to avoid this depletion of lithium, you have to go to even higher temperature, about 6,000 or so. And the upper points here is that you start producing lithium by other sources. So the figure makes sense. What doesn't make sense, so here's that data again, with people assume was the primordial abundance, but with WMAP or Planck, what you found is that the BBN predicted abundance is here, and you see that there's a big offset from there, sometimes known as the lithium top. This is the production of lithium-6 and lithium-7 from cosmic ray nucleosynthesis. So that's growing in time, and that accounts for some of this increase that you see here. So what's the reason of the discrepancy? I'm not going to go through all these in details, but you can talk about whether it's the nuclear rates, or there's some missing resonant reactions that could destroy the lithium. That's been studied pretty heavily. You can't do too much with the rates because they're the same rates that are going on in the sun. And those are the rates that are controlling, for example, the solar neutrinos, which are very well measured and agree very well with the prediction. So once you take into account neutrino oscillation. So there's not much you can do here. There's a lot of work done on stellar parameters. Are the temperatures wrong? Are the surface gravities wrong? Are the metallicities wrong? Are the rotation velocities wrong? The abundance depends on all those things, but that has also been studied very well and doesn't seem to be able to come anywhere close to accounting for this discrepancy. Stellar depletion, there were two arguments, which I'll get to in a second, why stellar depletion shouldn't have been operative. That's the destruction of the lithium in the star. So this was always discounted for reasons I'll say. So you can go on and do other things beyond the standard model things. You can imagine there's some new decaying particles in the early universe which destroy the lithium. Other things involving axions. You can say the fundamental constants of nature were different at the time of nucleus. You can get more and more exotic to try and solve this problem. Try and argue that it's probably not necessary. So why not depletion? Well, one is that if you're destroying the lithium by a factor of 5 in all of these stars, why is it a factor of 5 in every star? Why does every star seem to, independent of its initial conditions and its set of parameters, why does it always destroy it to the same amount? If you're going to destroy it by a factor of 5, sometimes you'll destroy it by a factor of 4, sometimes by a factor of 8, sometimes a factor of 2, and that's not seen in the data. So the fact that there's no dispersion in the data says that there shouldn't be depletion. The other is that there was the observation of lithium-6 in the same stars. Now, lithium-6 is much more fragile, and if you destroy lithium-7, you would completely get rid of lithium-6. You should never see lithium-6 in the stars. So just a quick thing on lithium-6 and some of these other elements. Lithium-6, here, is produced, these are again BBN production. This is that same dip that you saw earlier. This is a much wider scale here. There's the Planck value for eta. But you see, this is at the level of 10 to the minus 14. And beryllium and boron are all way, way down. So 10 to the minus 15, 16, 19. So these are not BBN produced isotopes. So this is just the values you get from BBN relative to the observations. So these things are not produced in BBN. These are produced from cosmic ray collisions. So you have protons and alpha particles in the interstellar medium, and they're hitting other alpha particles and CNO in the interstellar medium, breaking it up and producing lithium-6, beryllium, and boron. And that actually works pretty well. That can account for the observations of these elements. As I said, there was a time, maybe happy, maybe we're happier now actually, that the lithium-6 to lithium total was about 5%. And again, this couldn't have been possible if lithium was destroyed by a factor of 5. And the BBN abundance is 10 to the minus 4. So you can make models, as I said, of cosmic ray nucleosynthesis. And this is the data, for example, for beryllium. Here's for boron. This is what the models. So the models are, there's some fitting, of course, going into adjusting the parameters of the fluxes of the cosmic rays. But once you do that, then you're sort of all the other elements are tied. So they do a pretty good job. We've looked at this now much more recently, and again, there's a lot more data now. And the models, the cosmic ray nucleosynthesis models, do quite well. And this is what they predicted in the past for lithium-6. These were the observations, the two observations. This is what the model was. So it all made sense. Models predict they should see lithium-6. They saw lithium-6. So the lithium-7 shouldn't have been destroyed. And no dispersion, so that was the way it stood for a long time. First kink in that chain of armor was that there was some more lithium-6 observations, the two, I think, were somewhere around here, but now there seem to be lots of lithium-6 observations, and all with the same abundance. That's fine for lithium-7, but lithium-6, that makes no sense, because it's coming from cosmic rays, right? It should follow this line, not be flat here. So that was the first warning signal. And so the observers started to scrutinize these observations in a lot more detail, and found that not only were most of these observations not lithium-6, but all of the observations are suspect. You cannot be sure that any of these observations actually correspond to lithium-6. It's very hard. Now you're again looking for that little bit of isotopic shift between 6 and 7 in an absorption feature. So as far as we know, there's no observations of lithium-6. What we do know is, say, again, we have the model prediction. Now we have upper limits on lithium-6. We know at least that lithium-6 was probably destroyed. And we also have at least an estimate of the minimum amount that was destroyed. And you can then ask, well, what does that mean for lithium-7? So this was the prediction of lithium-7. This is where the data is. And so you can re-engineer it and move those points up by the amount of destruction in lithium-6, saying if lithium-6 and lithium-7 are both destroyed in the same way. It doesn't have to be that way, but that's model dependent. But now all of a sudden, these lithium-7 points could be as high or higher than the BBN production. So it seems there's reason to believe that there's depletion. Now there's been a lot more lithium data, lithium-7 data. So even going back to 2010, this was the picture I was showing you before, this flat part. Now going down to lower metallicity, all of a sudden there's a lot of dispersion. And you're not supposed to have that if it's primordial. So this should have been continuing out very flat. So now the question is, why is there dispersion here and not here? Well, so this is now 2018. This is still very low metallicity. I was showing you before between -3 and -1. But now, and so this is now 2019, and I think this is the full set between -1.5 and -4.5. If I showed you this initially, you wouldn't have said there's no dispersion. There's a ton of dispersion. So there seems to be a maximum lithium abundance, but there's no way that you could argue that, that there was never any destruction in lithium. So maybe there's no lithium abundance. All right, let me come now to the CMB. So Planck, this is the old, we can just look at the bottom. Planck 2018. Planck provides for you their likelihood chains, and so you can just take their raw data and do what you want with it. We had to go back to their raw data because Planck does these kind of fits as well. So this is capital omega times h squared. It's just little omega. This is their determination. This would be their determination of baryon density, the helium abundance, but the one they published makes use of a relationship between the baryon density and the helium abundance from BBN. If we're going to use it in conjunction with BBN, we have to take that out. Fortunately, we don't have to take it out. They provide the chains where that assumption isn't built in. So they have all sorts of data available for you, and you can take their likelihood chains. And this is just CMB. So this is just CMB data, and this is their helium abundance. So it's not bad. It's 24%, big uncertainty. This is about 4 times the uncertainty in the observations, and much, much higher than the uncertainty in BBN calculations. And if you allow the number of neutrinos to float, so this is here, it's n nu is equal to 3 flavors of neutrinos. Here it's left to be arbitrary, then you can fit for the number of neutrinos. And this is just the CMB data, what you get there. This is again just CMB data for the baryon density and helium abundance. So very tight scale here, 5.8 to 6.4. This is the BBN prediction. The thickness here is 3 sigma. So that gives you a little bit of an idea. And this is the prediction from CMB. Again, great agreement, but CMB alone does not do you very good on getting helium abundance. So this is what you get from BBN calculations in terms of likelihoods. So what's shown here, the purple are the purple here are the combined CMB BBN. So this using the likelihood, the Planck likelihoods combined with the BBN likelihoods. So this is the prediction for helium-4, very, very tight. Essentially, the only uncertainty there is the neutron mean, like I said. Deuterium is that. So that's again coming from the input cross sections. This has been reduced by roughly 50% because of that new cross section measurement. And this is what you get for helium-3, and this is what you get for lithium-7. The yellow are the observations. So again, the observations for helium-4 is something that you'd like to see improved. There's good agreement, but you'd like to see how does this collapse down when it gets narrow. This is the observations from the quasar absorption measurements, and there again you see that great agreement between theory and observations. This is just the CMB helium-4, so again, it's very broad. They get in the right ballpark, but they don't have any precision on that yet. No helium-3 measurements. I didn't talk about helium-3 is because helium-3 is produced in the Big Bang and it's measured, but it's measured sort of locally, and you can't have any confidence that that abundance corresponds to the BBN abundance, even though what's measured is about 10 to the minus 5. So the abundance that you see does agree with that, but helium-3 could be produced in stars. In other stars, it can be destroyed. So now you have to know the pattern of star formation in our galaxy and actually in our local area. And there's too many uncertainties in that. So we don't compare that directly to observation. This is the old lithium abundance, which now unshaded because you don't know that has to do with the primordial anymore. But that's this difference between these was the lithium problem. And these are just some of the numbers that correspond to, and you can see here the accuracy with which the BBN calculations give you for those abundances. Helium-4 is extremely accurate. So you can do various combinations of these likelihoods and get what the baryon to photon ratio is. So CMB only is this one. So that's the one that drives everything. CMB is very good in determining the baryon density. If you were just using BBN and helium, you'd be terrible. You don't even see it closing here. BBN and deuterium does pretty good. And then if you start combining the CMB with all these things, you can tighten this up a little bit more. And this is just some of the numbers for the different likelihoods that you might use. CMB only is 6.1, more like 6.13 if you combine everything. So BBN gets you a little bit better on the uncertainty, but most of the impact is coming from CMB. All right, so how can you use this to put limits on particle properties? So I said in the very beginning, I was talking about the balance between the weak interaction rates and the expansion rate of the universe. So H is again just given to you by the density radiation, same thing I had before. This is the neutron to proton ratio. So you start changing anything here, this balance is going to start getting destroyed. If you add new particles, for example, which is the thing that I'll be talking about, if you add new relativistic degrees of freedom, you'll increase rho, you'll increase H. That shows up here. Freeze out will happen at a different temperature, then the neutron to proton ratio will be different, and the helium abundance will be different. So that's sort of logic. And you can do that on number of particles or particle types. You can do it on the interactions of particles. You can do it on fundamental constants. If you change G Newton for some reason or G Fermi for some reason in the universe, you will again mess this up, mess this relationship up. So what's the sensitivity to the number of neutrinos? So the same plot essentially that I showed you before. This is number of neutrinos equal to 3. This is 2, and this is 4. So on the scale, it's pretty distinct. Which one will work out? Remember, the Planck is at 6 times 10 to the minus 10, so it should be right around here. So you can see that just by eye, if you're talking about integers, it's 3. There's less sensitivity, but not negligible sensitivity for deuterium. And again, lithium is not clear how you would use it anymore. So this is the same likelihood plots, but now allowing the number of neutrinos to vary. So you get a different result from CMB alone, but it's still very wide. It looks like you get better agreement here. The BBN prediction is no longer so sharp because it was sharp when you knew there were 3 neutrino flavors. If you don't know that and it affects the helium abundance considerably, then the prediction becomes much wider, in fact, wider than the observations in this case, but great agreement. You actually get a little bit less good agreement if you allow it to vary for deuterium, but it's not significant. and nothing going on down here, as you can see. So you can do the same trick. You can take the likelihoods and marginalize over the baryon to photon ratio and predict, if you want, the number of neutrino families. And again, CMB only, which is the blue, and that doesn't do quite as good. Now it's the helium abundance, and if you want to combine with the deuterium abundance, it does much better. These set of green lines are just all blown out. Other ways to combine it, variants. So now projecting down these likelihoods onto baryon to photon ratio, number of neutrino flavors. So this is BBN only with the dashed lines, and you combine it with BBN with CMB here. So again, great agreement. You see which thing has the most impact. So clearly, CMB, as I said over and over again, has a huge impact on the baryon photon ratio. Not so much on the number of neutrinos. And here's the opposite. This is just CMB alone relative to, and then with everything combined. These two are the same, by the way, the solid line. And then just again to see the numbers, what the numbers actually look like. Slightly different values for the baryon photon ratio, but again, nothing dramatic. Number of neutrinos, a little bit less than 3, but certainly within uncertainty, equaling to 3. The last one is the upper limit. If you assume that you know you have 3 and it should never be less than 3, the limit's a little weaker. And that's the upper limit is 3.18, and the one-sided limit is 3.226. So in case you're wondering, what does it mean to have a limit like 3.18? Because neutrinos are particles. You either have, they should be integer numbers. So I thought I'd just take a minute or so just to give you a flavor why that actually is a meaningful number. Because you could say, well, 3.18, it just means there's 3. It actually has more meaning than that. I won't go through this, but this is the neutrinos today. There is a neutrino background, just like a photon background. A photon background is 2.7 degrees. Neutrino background is about 1.9 degrees. And that's calculated in the standard model. It's just from entropy conservation. It's just that when the neutrinos decouple due to the weak interactions, and you conserve the entropy of the standard model particles, when you lose the electrons and positrons, so they annihilate, they give the energy into photons, and so the photons get heated up a little bit relative to the neutrinos. So the photons, had this not happened, the photons would also be at 1.9, but the energy from the electrons and positrons went into the photons, so photons are a little bit hotter than the neutrinos. So what does this limit mean? So for example, 0.226. Suppose we had 3 neutrinos, 3 other neutrinos, like right-handed neutrinos or sterile neutrinos, if you're familiar with the terminology. How can you do that if your limit is 0.226? Well, you could do that if the additional neutrinos or whatever other particle you might have is at a different temperature, if it's even cooler, because then they don't contribute as much. So if you have 3 of them and they have a different temperature and you want it to be less than 0.226, you can determine what that temperature should be. And from that temperature, again, using entropy conservation, you know when they have to decouple, when their interactions has to go out of equilibrium, and that tells you something about the number of degrees of freedom at that time. So here's a very rough plot of the number of degrees of freedom as a function of temperature, and it's just making jumps each time you cross a mass threshold, muons, pions, quark-hadron transition, quarks and charm quark, taus, bottoms, etc. So it just is something increasing, and the value when you have decoupling is going to determine eventually the temperature, just like we determine the temperature of the neutrinos. This is a little bit smoother of a plot when you start taking everything into account and integrating it, and this is a more modern version of that plot. And so from Borsiani et al., from using some lattice calculations. So if you wanted to have 3 additional particles present, they would have to decouple at a temperature of about 1.2 GeV. So relative to weak interactions, you should be decoupling at about 1 MeV. And then you can go ahead and do all the same thing and calculate the energy density of radiation. Basically, a scalar contributes 4/7 of a particle, a Dirac fermion, calculate and contribute 2, and then you can determine the temperature. So there is meaning for using these limits and going beyond the standard model. So as I said, the quick example that I just did was using for something like a right-handed neutrino. You can do it for the if you have extra gauge boson masses that comes from. So that's what determines the decoupling. You'd have to have a relatively heavy extra gauge boson that control the right-handed interaction. You can use it to set limits on dark radiation because they would be present to speed up the expansion rates. So there are limits on how much dark radiation you can have. Stochastic gravitational wave background, that's popular now. Things like tracker solutions, magnetic field, anything that's really beyond the standard model that has an effect during the period of nucleosynthesis can basically be constrained. And that's what the power of this is. So where are we going from this? This is the future, so I'm near the end. The CMB measurements on helium abundance are expected to get down to an uncertainty of about 0.005. Still not quite as good as the observations, which current are 0.003, and certainly not as good as the helium abundance from BBN. Number of neutrino flavors, the expectation is that you can get down maybe to about 0.09 in this, and this is what those likelihoods look like in that case. And you can again ask, what do these pictures look like if you have, so this is the same thing I showed you before, this is Planck 2018, this is what you expect from future CMB measurements. You see everything's getting thinner, we're assuming they get the same values. No. And this is sort of where you would like to go. There's a number here I didn't mention, this horizontal line at 0.044. The number of neutrinos, effective number of neutrinos, is not really 3. There are 3 neutrinos, but not all of the energy of V plus E minus goes into photons. There's a little bit that still grabs into neutrinos, and it goes from 3 to 3.044. So a little bit of that energy. So neutrinos are a little bit hotter than I said they were. So what you would like to do is you would like to be able to push these limits to be under 3.044 so that you actually see this 0.044 and measure it. That would be fantastic. And this tells you what kind of precision you need in the observations of helium to get down at that level. So depending on where you're coming from here, you probably need to get down to a level of about 0.006, 007 in precision. And as I said, we're right here, right now. So this is where we're hoping the future brings us. Okay. So let me summarize. As I said, BBN has come a long way from the 40s, from the sort of great idea that Alpher and Herman and Gamow had, predicting the microwave background. Fantastic bit of theory there. And now in combination, seeing how the two are working together, even though their origins were so closely linked in the 40s, that now how CMB and BBN are intertwined in testing early universe cosmology is fantastic. And there's really great agreement with deuterium. It's still very good agreement with helium, but if you'd like to get those uncertainties down. As I said, lithium-7 was problematic, but I'm pretty convinced that it's really is stellar depletion. What we're seeing in the stars is not corresponding to what the stars were born with. So the initial abundance of lithium probably is higher, and they have in situ destruction. So the wish list. So there used to be 3 of these cross sections we wanted. The DP gamma is the one that the Luna collaboration measured recently. We'd like these 2 to be measured because they still have large uncertainties and a big impact on the deuterium abundance. So with new measurements of these cross sections, you can probably get the predictions for deuterium considerably lower. And of course, as I said, we'd like to have high precision measurements. I think we know how to do it now to get helium abundance. So the standard model is looking good. That's all you hear. The standard model in particle physics looks good. The standard model in cosmology looks good. It's sort of depressing for everybody who wants something beyond the standard model. I mean, on one hand, it's good that there's something we do understand, or we think we understand something really well. But going beyond that, we know there's more than that. But nature's not giving us any hint. It's always saying, oh, you got the standard model, just be happy. So I'll leave it at that.
very much for bringing the IFUNAM courses.
I work with the London forest and particularly metal forests. So when you mentioned the deuterium and how it is technical in the intergalactic medium, I was wondering if there, well, two things. One, if there's something like a deuterium forest or something similar that you study.
Ooh, that's like jumping so far ahead of, I think, where they are now. So as I said, there's about 10 or 12 directions where this is even possible to do. In each of these directions, there is something like a forest. So it's not one cloud. I think one cloud, they would never be able to get it. So they actually use a series of clouds. I don't know if it's 3 or 7 or 8. I don't have that number in mind, but along a given line of sight, they are using several clouds to do the fitting to be able to extract the deuterium abundance. Without that, they wouldn't have it. So I think that's what you mean by a deuterium forest, where you have these stacked up. Yeah. So that's something, yeah, it should be there. But again, I think it's just a question of how easy it is to detect.
Okay. And second question is very similar. Is there a way to detect some sort of forest thing with other metals, or is there anything that can help us understand a little bit more about BBN
Nucleosynthesis.
with the other?
You don't see it. I mean, in all of these systems, you want to know what the metallicity is, right? So you want to be sure. So in the sense that the metals are important because they give you some indication that you haven't destroyed deuterium, that there hasn't been a lot of stellar processing. So you always look. You have to keep in mind that the deuterium abundance is 10 to the minus 5. And even in terms of metals, even low metallicity objects, there's much more metals, and the lines are sharper. You're not looking for an isotopic shift. So I think these are intrinsically hard measurements.
Yeah, so you need very new measurements for the cross sections. My question is, can they be calculated? I don't know, IPT or something.
Oh, that's dangerous. Yeah, you can calculate them, but how well do you know the theory? So I mean, I didn't go into this. So before the Luna collaboration came up with this new cross-section for BP gamma, there were other cross-section measurements. And then, for example, we basically took all the data that was available and did our own fits. The NACRA collaboration does compilations in its own, and you use them and compare to them. There's another group that also is doing something similar. Then there's a group that relies not only on the data, but also on calculation. So there's some theory in what these cross-sections should be. And basically they had higher cross-sections. And in fact, they were arguing that, well, the deuterium abundance is actually low. Actually, there's not quite matching up with what the BBN predictions are. And they claim that other things have to be going on, which to us was always strange, because you're saying you're not agreeing with the measured cross-sections, and now you're not agreeing with the observations, but you still think it's okay. And that's your argument for new physics. Then Luna came along, and we found that their theory estimates were too high. That actually the old measurements were good. Luna is even better, so you're going to use Luna. So yeah, you can do that, but now you're subject to the same worry that if you use some theory in here, you can do it, but I don't think that would give me any more confidence and precision. I really want a cross-section measurement with small errors.
So the measurement is brought from the deuterium.
The one that was done, yeah, was proton deuterium. Yeah.
You use that.
You mean for these? No, because different final states. You're thinking of like using mirror or something. No, these aren't mirror. This one is what, helium-3 or tritium, I guess, and that one's helium-3. And the other one is helium-3 gamma, but it's different final states, so they're not mirror images.
Questions? I have a question. So if you have the if you assume there are all the three neutrinos and say the temperature, background temperature would be of the order GeV, can you infer the mass?
Sorry, the background temperature when they decouple.
Yes, when
right.
they decouple.
Right.
Can you infer the mass from there, at least, or the sum of the masses or something?
Not of the neutrinos themselves, because here you're assuming they're relativistic at the time.
Yeah.
So that's all you know. What you can infer is that, so easiest example is they're right-handed neutrinos. There are new right-handed interactions. So there's either a Z prime that does the right-hand interactions, or you can have a whole SU2 right. Right. So if you have that, then what you can do is you can estimate the mass scale of the right-handed W and Z.
Okay.
And that's going to be in the TeV range.
The
TeV. In the TeV.
Okay.
Several TeV. Yeah.
Yeah.
It depends. I mean, it goes up very fast as these limits go down.
Okay. More questions?
Yeah, also there's a lot where you have the helium abundance, I think, and you say that the error, a very small error was coming mainly from the neutron lifetime.
Yeah.
But does error include the difference spin versus Otto, or?
I took that. I had that in poor Marcos. I had to sit through almost the same talk 2 weeks. 2 weeks ago. He had to hear this. I think if I go farther down. Okay, so this is what you're referring to.
Yes.
So the shaded region there is the PDG world average of the neutron lifetime. But if you go into it, you find that there are two sets of data, and here you see two different peaks. They don't quite agree. This is at a level that they disagree, so it's not crazy, but it's there are two different methods in doing this. And we did play the games of what happens instead of using a Gaussian that's centered around the shaded region. If we use this thing is called an ideogram. PDG used to show these for all their measurements. They sort of stopped now, and maybe you can still find them online. They're easy to construct from their tables. So this is what the differences in things that you would get. So this is the PDG weighted average. This is something I think I would have. This is not a function of neutron mean life, and there it is. So now you can see how much the helium abundance depends. And this is the plot I think that you were talking about. So you see, there's a little bit of a little hang thing here, right? There's a little ledge. That's the extent of the difference I'm getting. Okay. Thanks for the question.
Yeah. The last one.
Okay.
You also say that you can estimate standard model parameters. You say like you can essentially change it and see what are the constraints on these changes. There was a plot where you have delta alpha over alpha.
Oh, yeah, for the fundamental constants.
Yeah,
right.
Of course, alpha at 0, right? Or
alpha.
Yeah.
So the delta alpha over alpha it's from BBN. It's a little less. It's better than 10 to the minus 2 or so. Yeah. So it's the alpha at BBN relative to the alpha today. Minus the alpha today relative to alpha today. So it can't be too much different. Then it depends on what your model is for how you change alpha, and if it's not just alpha, but it's Y alpha electromagnetic and not alpha strong. So if everything sort of changes systematically, you can improve the limit by about 3 orders of magnitude. So it's about 10 to the minus 5 in any sensible theory.
Small question. You have this step graph where you have all the resonance, you're seeing how they change. What is the last one? You have the top, and then what's the last one? What's heavier than the top?
This is a very old plot. It's a very old plot. It's very uncertain. If you look at it closely, you'll see what it is. It's W.
It's W. Okay.
We knew W. We didn't know the mass of the top chord.
Okay.
This was, I probably made this when I was in graduate school.
Yeah.
So we didn't have any idea where the top is. Of course, it's not, I didn't even think of that, but as soon as you said it, okay, that's here it is. Oh, here it is.
What are you predicting there?
I don't know what I guessed. There's no numbers here, but it's somewhere between bottom and W.
More questions? More questions? So I think keep